load balancing, FJs and cows are each standing at distinct locations on his two-dimension farm. Each each cow gonna have a XY coordinates, and then you see here it's a totally 100 cows. Be careful with this n. It's 100. They're gonna tell you something. And the xi and yi's are positive odd integer of a size most. The upper boundary is b, and all this xi and yi is odd numbers. FJ wants to partition his field by building a long, basically fence. One is a north-south direction, and with the equation x equals a, and a is going to be even integer. So this fence will never get across any cows because all the cows' coordinates is at all numbers. And similarly, FJ also going to build a long east-west fence with y equals b, and b is integer as well. Okay, so pretty much is very simple setup for these questions. You can think about, get my annotate. So this is X, this is Y, and then you have a lot of cows, maybe here, here, there, and more, right? But totally gonna be 100s. And what you have to do is to help Farmer John to define this offense. So clearly you had to define these points, and this points is A, B in these coordinates. And here's the requirement. FJ wants to choose A and B, basically these points, so that the cows are appearing in the four region. So you can think about there are four quadrants. Of course, in the first quadrant, there are going to be four regions. And then you're going to have the cows at each of the region, four regions. So Farmer John really want to have the maximum number of cows appearing in one of the four regions. Let's say there's M1, there's M2, there's M3, there's M4. So here the M equals to max MI. So Farmer John is saying, hey, could you do me a favor? Try to deliver as small M as possible. In other words, you want the distribution of the cows in terms of number across the four regions as uniform as possible. So that would be the question. And also for the first of our test cases, B, which is the upper bound for X and Y, is about 100. Well, this is like telling you, you know what, go ahead and play with it. With n less than 100 and also with up bound 100, well, just brute force, quickly can take care of it. The really challenge is about the remaining test cases where the B gonna go to 10 to the power 9, 10 to the power 6. So that will making your algorithm, you're gonna optimize your algorithm to deliver that. So inputs, you're gonna have two integers for the first line. The n gonna tell you how many cows, and the b gonna tell you what is boundary. So here's seven cows. So next to 7 lines, including the coordinates of the 7 cows. And as to the xi, yi, the upper boundary is 10. So every cow is, bounded in this from 1 to 10, from 1 to 10. And you're going to have 7 cows, and you're going to go ahead and play with it. Going to find the points A and B, so then they're going to define the fence, right? Fairly enough. So that is a question. So let's go to the coding doc. Let's deep dive this question. So far, I assume everybody, this is my requirement. Everyone is mandatory to read the questions, because otherwise it's just going to be such a pain for you to go back to understand what the question is. All right. Now let's go ahead and talk about the brute force. I guess everybody understand the problem statements is to find A and B so that the total n cows can be divided into 4 regions. What is 4 regions? Firstly, go to 1 to what? A minus 1. And the second one, this is X, right? So this is X direction. The Y direction going to go from where? Oh, I would appreciate people really could show up on time. Otherwise, I have to, admit people into the sessions. I appreciate that for next sessions. People just show up on time. And for the y is go from 1 to where? To b minus 1. As you can see that, the first region is about this portion. So x go from a1 to a minus 1. Since a is going to be even number, all the cows going to have x or y, which is odd number. So that's why you can bound the x is 1 to a minus 1, and y is 1 to b minus 1. So this is going to be the first region. What about the second one? Second for the x, going to go from, maybe you want to look at M1, right? What is M1? M1 going to go from a plus by 1 and to the bound. The bound is going to be the b, right? As to where the b is, well, look at the inputs. So that's going to be the b. And for the y, you're going to have is from 1 to where? To b, right? So pretty much with that, you can define the third region and the second region, so on and so forth, right? Third region and the fourth region. With these questions, you see, we can definitely go ahead with the brute force. The reason is, if you look at the inputs, the n is less than 100, right? And also, it also telling you that for the beginning several cases, going here, it said for the beginning cases, what is boundary of the b? It's just a 10 square. So if you go back to here, you have 100 cows at the maximum, and all these cows are bounded in this 2D square, where 1 to 100 for the x and 1 to 100 for the y. So now you tell me, for this algorithm, just brute force, it's going to be well defined. It's going to be this. The brute force is going to be for what? For each possible A and B in the farm. And what you're going to do is what? You're going to go ahead to figure out with M1, M2, M3, M4, and just go ahead and count how many cows. So for inside of this 4, so you will have to find the total cows numbers in M1, total cows in M2, and total cows in M4. And after that, go ahead to define the maximum one. So the maximum is going to be the max EI. And with this M, you go ahead to update. Maybe you already have the answer, which is, max, or just say global min solution. At the beginning, just define the n. Of course, the answer cannot be n, definitely. And with that, you update these global min solution as necessary for whatever m you could have. So that pretty much is brute force. It's not challenging at all. I mean, for beginning cases. The reason is that if you look at the time complexity, for out of 4, for all possible points in the farm, how many of them? Just O of n, right? 10 square at the maximum. And what about the inside? Inside one, folks, for the inside, first of all, for the possible A and B, actually even less than 10 square, because all the walls at the A or B, which has to be even number, actually just even less than that. But it's not going to be just n. It's actually n square. Because for the x, you can have from 1 to 100, right? For the y, it's going to go from 1 to 100. So you're going to have a 10 to the power 4 coordinates in that square. But remember, you can only land on the points where it has to be even number. So it pretty much you can drop down. That is a 50 square. I mean, still just put down as n square, as that still should be fine, which is in this case is 10 to the power 4. And then when you actually, it's a b. This ends the numbers cows. Actually, this is a b square because the maximum range is defined by this b. So this is b square. As for the beginning cases is 100. So this is 10 to the power 4 is nothing, right? And then for your inside is counting for each 4 to deliver the total number of cows in each region. Then how many of them? It's still on the b square region, right? And then you're gonna keep going and count. So total time complex for this one is gonna be O of a b square, and the times of one of the ways you're gonna count how many cows in one of the regions. And so this is gonna be easy, right? So what is that? Is a b to the power 4. For beginning cases, I guess nobody care. This one just deliver is a 10 to the power 6, 10 to the power 8, right? Still, still doable. If any of you already tried with that, you might just passing less than half of the case. Half of this one is a 10 or 12 use cases. You may just passing the beginning ones, because to be honest, 10 to the power 8 is actually a lot, given the time complexity and also the absolute time the user can allow. 10 to the power 8 is really something you try not to you know, deliver that. So starting from that, we really need to think how to optimize. For this question's optimizations, let's take a look at two portions. One portion is we traverse all possible location in this farm, but the very challenging fact is that this farm could be very large, as a B can go up to 10 to the power 6 for the B, for the later use cases. And the 10 to the power 6 is going to deliver you 10 to the power 6 square. This is a 10 to the power 12 levels of points. If you go ahead with the Sprue Force, that's going to be crazy. For 10 to the power 12, you can never pass in the use cases for the later cases. So definitely for optimization, we identify for the first outer for loop, we should not use that to brute force each position points. Now the question is, we have such a large farm, and we only have a 100 points because n is 100 as a cap. So how could we better optimize the algorithm? Because you see that if you pick the points for A and B, gonna build up the fence. You can extend the line. You can see there's a fence build up. And since this is so sparse for the cows, distributed, well, I can also make the fence to be set up here. It gotta be the same answer, isn't it? Because there's so many areas, so much footprint where you can put down the fence. So the first thinking you should have is whether or not you can compress the cows, make the cows come get closer while not violating the algorithm. You can place the fence, right? So for this part, let me give you example. So let's say this is 1. This is 10 to the power 6. This is maximum of the B, right? And same here, this is 1. And this is 10 to the power 6. Now look at this. Let's just go extreme situation. Now you only have 4 cows, right? Let's say the 4 cows is, look at here's, let's say 2, 4 as a location. And this one is, you know what, is 1,000, and then 550. And then you get another points. Let's just go ahead with this. Maybe here is 200, and then 10, and then 3,000. Okay, and then another points here. Let's say this one is 700, and then what is height? Okay, 4,000. Okay, like that. Now we have a 4 points here. Let's say this is P1, this is a P2, this is a P3, this is P4. And you can see this farm is so big, and you just have a 4 cows. And remember, for the Sprue Force, what we do is we are, you know what, just go ahead with each positions, bounded by 1 to the B with whatever, as long as the even number, we're going to go ahead and creating the fence and count M1, M2, M3, M4. But clearly, we identify the redundancy lies in that there's so many places you can actually avoid, because you stand the fence, drawn points here, make no difference. You set John fence John point here. That make no difference, right? Because the cows are so far away. So one of the optimizations in order to cut down the time is we trying to not to, spend a lot of time on the free footprint. But how to do that? Like the word I already mentioned, why don't you can compress the cow in terms of location in such a way? Do you think you can actually have another version of a 2D plan? Where here is, you only need to put the first cow, which is 24 P1, at 1, 1. Let me use a different color. So this is going to be the P1. So P1 is right now is a 1 and 1, and corresponding to 2 and 4 in the right side. The second cow, in terms of X, is going to be 1050. Why don't we put this cow at the location 3? And the second cow is over here. So actually, I'm not exactly bear the example. Example said that all the XY for the cow location should be odd number. So let me modify it a little bit, otherwise people are gonna get confused. Let's say this point is 3, this one is a 5, because it said it should be odd number, right? So 3 and a 5. All right. This one 1001 and a 51. This is 4001 and it's 701. This is 201, 3001. All right. So now all numbers. All right. So again, 3 and a 5, we want to put at the new plan, which is 3 and a 5. So 35 is corresponding to 1 and 1. The second one is for 1151. Well, we're going to put this folks at what? 3 and a 1. So this is going to be P2. And corresponding to 1001. Oh, actually, no. Sorry. It has to be 5. Let me explain. The reason is that let me redo this part. The idea here is, first let me briefly deliver the idea here is, we're trying to compress these 4 cows to be closer as possible, but still bear the similar relative order. In terms of P4 is on the right side of P1 and also overall higher than P1. So we want to keep the relative order into this new 2D plan. So with that, we're going to scan the X for all the cows. So the smallest one is P1, 3 and a 5. And so we put P1 at 1 for now. And also, in terms of Y, you see 3 and a 5 is smallest from original one. So that's why we put a P1 as a 1 and 1 in the new 2D form, 2D plan. So the second for this is 3. So for this 3 is going to correspond to the P2, because P2 is 201, 3001. So we're going to put that as a location 3. So that one we're going to have is, which is a P2. Let me use a different color, right? So P2. For P2, 201, right? So we're going to put that as 3. And for its of Y, really depends on the order. You see 3001 for the P2 is the third one, among the 4 cows. You see, we have 5, 51, 3001, and then 4001, right? So this P2 is the third highest in the Y. So we're gonna build our Y here. So this is gonna be 3, and then this is gonna be 5, and this is gonna be 7. So since this one, as we already reasoned, is gonna be third one. So the third one, so this folks, we're gonna put at 305. And this looks corresponding to the original one is going to be 201 and also 3001. That's a P2. Then let's go to P3. P3 is 701, 4001. In terms of X, it's a third, 3, 201, and 701. So you tell me, we're going to put at position 5, right? So this folks belong to 5. And as to the Y, 4001, that's the highest. So we're going to put at the 7. So this is a P2, and then this is going to be P3, right? So this is a 5 and a 7, and the original one is a 701 and a 4001, right? Again, people should follow here is we're trying to compress all the cows into new 2D, definitely much shorter one, but you have to keep the relative order. Otherwise, there's no point doing that, right? And then the last one is a P4. P4 is 1001 for the X, which is the maximum. That's why this folks going to belong to 7. But 51 is the second smallest. So you're going to put the P4 at 7 and 3, right? This is going to be P4. So which is a 7 and 3, which is originally is going to be 1001 and 51. Okay, now we compress the distribution of all the cows into a much shorter farm, much smaller farm, and of course everything is still again is all number. You see that, but much closer to each other. That's one thing. The second is main point is we compressed the distribution to be a very tight distribution here. The reason is that we just trying to cut down the time to place the fencer joint point on the even points. So now, if you look at, if you still go ahead and using Sprue Force, now it's much easier to put your fence gonna be 2 and 2, right? And then 4 and 2, and then 6 and 2, and then what? 2 and 4, so on and so forth. And it definitely is much less time in terms of traversal, right? So that's the first area you need to optimize the code for optimization. So hopefully everybody follow here. So let's compress the distribution of the cows and maintain the relative order, relative positions. In terms of if it is on the right, it's still going to be on the right. If it is on the top, you're going to do it as a SAM. So that's the first optimization. Is there any other optimization we can do? Still go back to the Sprue Force. Before I do that, let me try to get down this picture here. Okay. So look at this Sprue Force. Now we optimize the for loop, which is really something. Now, what about the inside? You see the inside is, the thing is like that. I need to place the fence join point on any, open footprint with even integer number. And then I'm going to go ahead to count any cows in that region and all the other 3 regions. I have to do that again and again, no matter at what locations. Do you see a lot of repeated calculations? Of course, right? For example, if I put the fence somewhere, let's go to our shorter version. So if you put your fence here, you're going to count the P1, right? Then if the second round, if you go to putting fence here, you gotta go ahead to count the P1 because this is the bottom left portions. You gotta repeat counting it, like a start over every time. So this is clearly a repeated calculation for people who already take my bronze and a basic server class and also advanced server class. So we use the word called pre-processing. This is a typical use cases we can do pre-processing to avoid the repeated calculations. Then how to do that? So let's the first document for the second optimization is um, decrease the repeat calculations calculation uh, in Sprue Force inner for loop. In counting cows in each of 4 regions. Okay, that's the second area we want to optimize it. So the way for so here solution for the first one. So let me document. We already did that. Just by pre-processing. So this processing is like this. So let me give example here. Let's say, let me give example. Maybe let's using let me clean this. So we don't need this anymore. Okay, let's see this example. So the idea here is we want to have a 2D array. So let me type in that. I will run example with you folks to understand that. So here's, let's have a 2D array called count, and with the size accordingly, right? So the idea for this account, the fiscal meaning for INJ. So this is indicates the number of cows in the region for X coming from 1 to I. For the Y coming from 1 to J. Okay, so for a point I and J, let's say here's, and then for this example, you're going to have only P1, right? So this is the number of cows in the region for these portions. And the reason we want to maintain such a 2D array is we could avoid counting or calculating the number of cows starting over from the region every times. We can actually build upon from previous countings in the left and also the below position. So think about that. If this is a physical meaning, now if I want you to figure out for count I and j plus by 1, what is that? That is, you are already have looking at it here for this region. There's a 1 cows. Now, how many cows for I j plus by 1? You're gonna have a little portion here. Can you actually build upon overcount I and j to deliver that? I think so, right? So let me give you the formula. So here's a count I and j in general. All right, let me remove this first of all. So this count is equals to count from previous round, I minus j, j minus, I minus 1, j minus 1. I j minus 1 and minus count I minus 1, j minus 1. So this is a little bit very closer to the exclusion inclusion. And the idea here is if you already have, let's say, let me try to show that. If you already have, this is, you know, how to make this better? Let me remove this first of all. Okay, so this is originally I and j, right? And here's I and j. You want to know how many cows within I and j all the way to the origin points. But this is relies on I minus j, relies on this. Let me find a different color. This relies on I minus 1 j, right? Because the total the total blue footprint, including the red footprint, and also plus a different color here. This green footprint. And then clearly we have an overlapping here. And this is the answer from previously I minus 1, G minus 1. So you want to subtract this portion. And then adding this little portion, which is what? Whether or not we have a cow at I and j. If there's so, just add by 1. Right? So that's why you're going to add, instead of equal, just plus equal. Or just write this. Plus count I and j. All right. So this is per processing. Very briefly, I assume people already can refer to the earlier lectures when we discussed these chapters. And the I and j again count. I and j stands for the number cows within these portions, and then that relies on the previous round. You get number cows at I minus 1 j, the red, and also add previous round where you get the total number cows at I j minus by 1, this blue, this green footprint. And then add together, you have to subtract the overcounting parts, which is minus I minus 1 G minus 1. And then you're going to have one piece and count only one time for the total footprint and add on the count I and j, whether or not you have a cow right over here. If so, just add by 1. Just add on that. So with that, so you only have to traverse the open space one time instead of many times, right? So that would be the second area to decrease the repeated calculations. Okay, so briefly, let's summarize before we code it out. The first one we optimize that is, let's cut down the times we start to traverse. We have to traverse the open space so that we can decide whether we can get a good answers by putting the fence at A and B. The challenge for this question is that there's so much free footprint to place the fence. Given that reason, so we need to cut down the footprint so that we can have such a shorter or smaller footprint of the farm. The second is, instead of every time we have to count start over for the cows in all regions or 4 regions, we're going to use improved processing. We're going to basically trade off the space to record the answer from previous rounds so they can deliver for the current round. Okay, so people can follow our coding process. Hopefully, I want to deliver within 10 minutes. But this is a very typical bronze level questions, but only associated with pre-processing. And the second part is, how would you going to associate from previous coordinates to be a smaller or tighter distribution coordinates? So let's see how that to be coded out. So this is just one of methods, actually. The way my class, the way to deliver the questions, should be different flavor. One is starting from Sprue Force. You understand where's the redundant, where's the repeated calculation, and then go ahead and optimize it with either algorithm or data structure that can be covered in our lecture sessions. The second is also is about the solving approach. We have a simulation, we have a starting big, and you list it in our sessions. So this is even higher level than the algorithm. The way you approach the problem, the way you translate the problem down to component levels. But actually for this question, I wanted people to think there are other methods to resolve it. The other method, given the time, I just can tell you the answer. Center of mass, COM. You can treat this problem like that. Then each cow, since this one asking for number of cows, so let's treat the cows who have the same weight. Now, you kind of have a pie or a square pie or something, right? This one is like a holder, is massless. And then you're going to place one cow, let's say a chocolate bar, a chocolate point here, and here is there, that, and here, and just 100 points. And each point has a unit weight 1, all right? Now, you can find where the center of mass. If you guys already started with AP Physics 1 or pre-honor physics, I guess so, right? You guys are grade 8 or grade 9. Then you can quickly calculate, given this plan or plate with 100 points, each point just have the mass as 1. Well, easily we can know where's the center mass. Maybe the center mass is over here, right? For this plane, the center of mass is here. What is center mass? The center mass, you can treat these, objects as a single point. They can represent the whole kind of stuff. So that's the center of mass. And that center mass, you can go ahead to calculate it, which is the center mass equals the total mass, which is n, right? And then for each one, go ahead and add up its x coordinates, and similarly, you can get a y COM, and similarly, n, and add up. This is going to be yi. Now, you have the center mass as here, so you know, well, the fence should be somewhere but nearby, because your center mass not necessarily is an integer number, right? So your center mass going to calculate might be floating number. That's 1. 2, the center mass you calculate, if it's an even number, if it is integer number, that might not be even number, because the restriction is the fence should stand on the location where x and y are integer number, but even integer number. So when you get down to x COM, y COM, all you have to do is find the nearby coordinates where it got x as even, y as even, and go ahead and traverse all the 4 regions. So you can have the answer also from that flavor. Right? So any question for now before we code it out? We kind of extend the session a little bit longer. All right, if no question, let's quickly code it out. Let's just go ahead and creating the class, since this one is called what? For this question is called balancing. Is that right? Let me double check. All right. Okay, balancing. Okay, so go ahead and creating a class called balancing. And go ahead and using template. This template is basically the way to read inputs and output, and mix the output, and then so they can upload for a check. All right, so if people have a question regarding template, just talk to me offline, but we don't want to spend time here. So first of all, you need to record the inputs. Remember, you got inputs from, first is n. So this n is what? Total cows. Total cows number. And the next one is upper boundary is b, right? Okay, this is all right. So that's the 2 numbers, and also you need to record the inputs, right? For all the n cows, each cow gonna have x, gonna have y. You had to record it. So this one you're gonna have a 2D array just called inputs, and this one depends people. You want to starting with the index 0 or index 1, whichever. Just make sure it's consistent. And for this one, let's just starting from 1. And with that, go ahead and record the cows. This is pretty much very boring wash and bottle parts. Let's go ahead and deliver that. So For each cow, you have record is X. All right. So this inputs. Okay. And after that, you can close the input file. So now we're going to discuss the algorithm here. So what's the first job, folks? Compress the cows into tighter distribution, right? Remember the example I showed you, how exactly compress that. So the way in that example, remember what we do is we have to place the X from the original farms in ascending order, and then we're going to put that into our new farm, which is starting from 1, 3, 5, 7, basically all number, and going up. So that's why first thing you have to sort this inputs based on the X. So then you can have a pair of what? So we need a kind of pair. This pair can telling us what is X from origin to X to the new. Remember that example we started from, the first one is 3 and 5, the cows, 3, so go to 1. And 5, go to 1 for the Y. So we need a pair to tell us for a cows from original form, given the original X, what gonna be the new X in the new form. So you had to deliver that. To deliver that, definitely first thing you had to sort the inputs based on the X into ascending order. And then you can set up the pair. Now, what data structure gonna hold this pair? It's gonna be very easy, just one D array. You can deliver that, right? So let me do that is first let's have the one D array to hold this pair. It's gonna be int. Let's use the name is called X record. And what is gonna be size, folks, for here? The size for here is the up bound is B, right? And then you can go ahead with B plus the 1 since we're starting from 1, okay? And what else? Also Y, right? You're gonna have Y record and it's gonna be new int and B plus the 1. I'm making sure, did I record? Okay, good. All right, and then you're gonna sort it out. So first gonna sort, you're gonna sort the inputs based on the X, right? This is should be like what I want to say is if sorting is due a area that you're not very confident with, you should go ahead into the lecture chapter, I believe chapter 3 or chapter 4. Go ahead and review that. And this is very basic in your coding, and making sure you don't spend any longer time in terms of doing this. All right. And clearly for this util, you want to input everything. Okay, so see here is we sort the inputs based on what? Based on the X, right? And after that, what you need to do is build up this pair. So you have another for loop into I, go from 1, since we start from 1. And I kind of less than, how many of them? Less than N, less than I. And so here. And R plus plus. Remember, for our new form, again, the XY should be odd for the cows. So here we're going to have an X record where inside is going to be inputs where for the first I and also for the first 0. So what is this? Inputs I0, that's what? That's your original X, right? Now, we're going to have a new X to assign to that. What is new X? 1, 3, 5, 7, going on, right? That's a arithmetic sequence. So 2 times I minus by 1. So the first I1, you assign that to 2 times 1 minus 1 is 1. For the next one, it's going to be 2 times 2 minus 1, going to be 3. So working well, right? So you set up the pair for the X and also the Y. So for the Y, you had to sort again, right? For the Y into ascending order. So basically copy this code going down here and just change a little bit, which is 1 and 1, right? Now you sort this input based on the Y, all right? And also set out the pair, just copy this and go down here. And then for I, you just change this to be Y, and don't forget change this one to be 1. So inputs I1, that is the original Y, and also you assign a new Y. So far making sense, right? Right, making sure there's no problem with that. Okay, and good thing that we set up the pair. What's next? What is the next step? So next step is you go to your you need to record the cows. You just set up the pairs. You haven't actually labeled the cows in your new farm. So first of all, you need another 2D array to represent your new farm, which is rec is going to new int. What range for that? So go ahead and define the range. That's going to be 2 times n. Why is that? Because maximum you're going to have what? Maximum you're going to have a 100 for n, right? Now we assign this new cow to be 1, 3, all the way to 100 times 2 minus by 1. So that's why for the range you put it 2 times of 100, just be right. So that's why this is going to be range, this is going to be range. And come down here, and then you're going to go ahead and making sure you label that. So here I go from 1, I less or equal to n, and I plus plus. And for this transversal, so you want to record what is X. So from the inputs, so here's inputs I0, that is original X, and then that gonna tell you a new X from this pair. This new X gonna be assigned to the X. Actually, you don't need to do that, but just for demo, I just want to make it clear. And Y is gonna go ahead and Y rec and inputs, and this one gonna be I, and it's gonna be 1, right? And then you can label that this a rec and add this given X and the given Y, just put as 1. All right, so up to this level, so you successfully compressed a very wide distribution of 100 cows into a rather tight distributions. And for each possible cows, the minimum, space is at least separated by 2. So you still have the even number there to put them fast. For line 11, there's questions for y11, yn plus by 1. You can go ahead and put an n. I just want to start with 1. Because with the question inputs, the cow never can have a position at 0. So I want to start with exactly start from 1. You can go ahead with the 0. It's also be fine. Okay, so continue from here. What is next? Next is going to be the second optimization, so-called pre-processing. So for this pre-processing, we want to deliver a 2D array with I and j, going to tell us so far how many cows for the square from the origin to I and j. So with that, you can go ahead creating another 2D arrays. It's just be fine. We'll not be limited for these questions. Or you can do that in place. You can go ahead using a rack. Why not, right? Since you're going to traverse your 2D for your X, for your Y, basically line by line and going up, and then you can reuse your rack. Okay, so for that one, you can go ahead with the int I, go from 1, and I gonna less than range, and then I plus plus. And then for the 4, int j, starting from 1, and j less than range, and j plus plus. And now go ahead using that function. Recall that function is I and j gonna be what? Gonna equals to rec. What is the left, which is what is bottom? I minus 1j. The other way, by the way, the reason I start from 1 is you do not have to worry too much on the boundary. For example, here's if you're starting with a 0, so you should deliver another line basically to because you don't have any cows below 0, right? So it's another nice part you can start with 1. And another is a rec. Here is I and j minus by 1. And don't forget to subtract the overlapping part, which is rec I minus by 1, j minus by 1. And if you have the cows at I and j, I'm sorry, have a cow at I and j, and go ahead and add by 1. So just go ahead and put a plus minus, sorry, plus equal. Then you're going to have a rec I and j, so here being maintained as so far in this traversal from 0, 0 to I and j for this square, how many cows are there? Okay. Then what's next? The next is just the final step is just go ahead and traverse all the open spaces, right? And figure out the number of cows across all 4 regions and figure out you need to update the M or not. So here the result's going to be the result going to return. So put down here and then go ahead to what? Traverse all open spots at even number. So you're going to have a 4. For I, going to start from where, folks? For the I, in your new farm, you put your cow start from 1. So it has to start from 2, right? And I going to less range. And what is the next one you want to traverse for your X? Going to be 4. That's why I plus equals 2. Okay. And then for your Y, into J, going to go to 2, and a J going to less range, and a J going to E plus equal 2, right? So this is all open space spots at an even number. Now, go ahead to count. First is the bottom left. If you have a cross in there, you're going to have 4 pieces of cakes. Bottom left, bottom up, bottom left, and top left, top right, and bottom right. So what is bottom left? Rec and J. That's our physical meaning for rec and J, isn't it? And then what is the top left? Top left going to be rec at I and a range of minus by 1. I mean, that's upper boundary. And then subtract that by I and j. And then bottom right, going to be what? Going to be rec. Then the maximum range for the X is going to be range minus by 1. And j minus rec I and j, right? And finally, for int top right, going to be, so this one I think we already discussed. For the rec, going to be range minus by 1. So range minus 1, that's the maximum you can go. And then what? And a minus. Rec I range minus by 1. And then what? And also subtract what? Rec and also the other portion with the range minus 1j. And clearly, you over subtracting one piece of rec on a j. There you go, right? So this is another driver why you want to use in pre-processing is when you traverse to get the answers, you can just go ahead and using one traversal and get it down. Okay, then how to update the results? Update the results, which is figure out what is the minimum, what is the maximum of among the four numbers, and compare with the results. And clearly, the result initially you cannot put 0 because you want to find the minimum results. So the results gonna be the math minimum results, and then you're gonna find the math maximum, and for this A gonna be math. You can make this just go ahead and you don't have to write into one lines, and just making sure it's clear. Bottom left and top left, and for this one math maximum, bottom left, top left, and bottom right, and top right. Okay. Bottom left cannot be resolved to the variable. What's going on here is bottom. Okay, there you go. We have a typo here. We got BMT. Okay. All right. Now the right? So you get the maximum of among the four numbers and compare with the results. If it is minimum, go ahead and update it. And now I'm sure pretty much we are done with it. And after that, after traversal, pretty much you're going to get the results. Now, look at this code. What's going to be the time again? So this time you cut down the outer for loop from the b square. For now, it's just n square, right? It's very nice. This is a lot of cut down in terms of time. And also in your traversal. For this traversal, we use in processing. This is just one round. Not necessarily very advanced your time complexity, but just one round of traversal. This is going to be very important when you guys promote it into code. Even at the same time complexity, because the overhead behind your algorithm, the total time has a limit. So any area you can cut down shorter, go ahead, cut down shorter. Before we submit the code, let's go through the code, making sure there's no problem with it. So we record N and B, which is inputs, and then we kind of maintain inputs. Physical meaning inputs is just record what's been given. And we're starting from 1 because make it easier for us to do with pre-processing. And there's nothing here we need to spend time with. Just record that and then close the file. And then the first one, we're trying to compress the count into title distribution. But we have to know what is a pair, what is the mapping, basically, from the origin to the new for the X. So we have a 1D array to record that. And we set the largest range is b plus by 1, which is definitely is okay for USACO for this level. And then you sort it out the inputs based on the X into ascending order, right? And after that, putting that, make the mapping. So you're going to have X record the old X. Now you're going to have a new X. And similarly for the Y, you got to sort it out based on ascending order on the Y, right? And we look at the 1, I1, 1, I2, 1, it's all right. And then you're going to set up the mapping for the Y. This is the old Y. Inputs I1, this is new Y. Now you have an I rec and Y rec. And this one is you had to literally label the cows in your new farms. And you know the range is 2 times n because you compress it already. You only have n cows. And the range is going to be 2 times n. And with that, you're going to traverse, for this for loop, you're going to traverse for the X and for the Y. You get the X and get the Y, so label that as Y, your new farm, which is rec. After that, you want to do pre-processing, but we're going to do that in place. And with that, you're going to traverse I, going to traverse J, so on and so forth, and then maintain that rec on the J. So here's a plus equal, don't forget about that. and the rec I minus 1j, and plus the rec I j minus by 1, and minus rec I minus 1 j minus 1 is perfect, right? So that's pre-processing. And then finally, you're going to traverse one more time again to find the answers. So you only have to traverse the open space where the integers as x and as y. So I gonna go from 2, j go from 2, and don't forget every time you need to add by 2. And you're gonna have this bottom left, ij, bottom left, top left, you're gonna I. So here, range minus 1, that's the top boundary, and minus rec and j. And the bottom right is you're gonna have the x boundary is the range minus by 1j, and minus rec I and j is looking good. And finally, the top right, you're gonna have the maximum range minus 1, range minus 1, minus rec I, range minus 1, minus rec, range minus 1j, and also add up rec and j. And finally, you're gonna update the results and find the minimum and update the result as necessary and based upon the maximum. Let me double confirm here. There's error as before, bottom left, bottom right, and top right. There you go. So that would be the code for balancing. So let's quickly upload that. And potentially there could be error that's going to debug accordingly. File missing. Let's see what's going on. Let me go down to. So I don't think we put the right file name. That's why you see here the balancing. We should using balancing, and here is going to be balancing out. Okay. Now try again. Exactly right. Give it a try. There you go. Like I said, with the beginning cases, it's a rather not challenging since the B is really small. And one more thing is, folks, if you guys try this question, the limitation actually, hard limitation for this question is not that much on the time, is actually on the space. You see, for the later, for our methods, since we compress everything is such 100 square, so the space consumption is nothing, less than 40 megabytes. If you do not compress that or use an alternative solution way to cut down that, you will not get past due to the space. Actually, you're not even checking on the time. Space will not allow you to do that because you're gonna have a 10 to the power 6 square for your space and also array. Think about it. It's not never gonna allow you to pass it. So that would be the area. That's why we're gonna have one of the two optimization to optimize the code. All right. So it's very challenging to cram questions into a lunch break session. I appreciate everyone's time. This is also a sampling of my sessions, classes, as to how we build up the curve. This is just a part of it. Like I said, starting with the Sprue Force, it's great. Start with the Sprue Force and then identify the area of redundancy or repeated calculations so they can further optimize it. All right. I think that would be a full demonstration for these questions. I hope everybody can have that as a practice if you haven't finished these questions. All right. This is already 1:34. Appreciate your time. Any question for now I can answer? All right, folks. Just no questions. And then I'm going to see you guys next week. Bye-bye.